In this video, I will talk about our work named System Stability under Adversarial Injection of Dependent Tasks. This is a collaboration between Vicent Cholvi, Juan Echague, Antonio Fernandez Anta, and Christopher Thraves Caro. In this work, we consider a model of jobs formed by dependent tasks that have to be executed in a set of servers. In our model, we consider a dynamic system in which job requests, or jobs for short, are continuously arriving, but instead of assuming stochastic job arrivals into the system, in our model, we assume the existence of an adversary that has full control of the job request arrival. We call this model the adversarial job queuing model, and the three main components of a system in these models are a set of end servers, an adversary that we denote with this A, who injects jobs in the system, and a scheduling policy, which is the criteria used by the servers to decide which task to serve next among the tasks waiting in their queues. The system evolves over time continuously. In each moment, the adversary may inject jobs to the system while the servers process those jobs. Each job consists of a finite set of tasks and a function that determines dependencies among tasks. In the example, job K consists of 4 tasks, and the feasibility function of K is given by the picture. So K1 and K2, for instance, in the example, do not have any dependency. That's why they are assigned with the empty set. Therefore, they are feasible from the moment in which job K is injected. On the other hand, K3 depends on K1 or K2. So K3 will be feasible when either K1 or K2 are complete. And finally, K4 depends on K1 and K3 or K2 and K3, which means that K4 will turn feasible either when K1 and K3 are complete or when K2 and K3 are complete. On the other hand, each task Ki is defined by 3 parameters. Si, which is the server in which Ki must be executed. Di is an activation delay, and Ti is the processing time of task Ki. So in order to avoid trivial overloads in the system, the adversary is bounded in the following way. If we consider, let NSI be the total load injected by the adversary during time interval I in server S, then for all servers and for all interval I, this amount of load, NSI, must be smaller or equal than R times the size of the interval plus a constant B. The parameter R is called the injection rate of the adversary. Every task waits in the queue of its corresponding server, and in each server, a scheduling policy specifies which task to serve next. Some examples of scheduling policies are first in, first out, last in, first out, nearest to go, or farthest from source. And we are interested in the stability of a system. And a system denoted by SPA, so the set of server S, the scheduling policy P, and the adversary A, is stable if the size of all the queues of the servers in the system are bounded by a constant that does not depend on the time. It may depend on the parameters of the system, for instance, the injection rate of the adversary. But the important thing is that this constant M in this case, it does not depend on the time. Okay. Hence, our results are related with the stability and the instability of systems. In particular, 2 of our results, these are not all our results, but these are just 2 of them, In particular, we show the stability of any system that has longest in system as the policy, and where the injecting ratio of the adversary is smaller than some parameter that some constant that depends on some parameters of the system. I'm not going to go deep into the meaning of that term, Tmean divided by Tmax plus Tmax, but the important thing is that we chose stability for systems that have longest in system as the scheduling policy. On the other hand, we showed that if a system has first in, first out as the policy, no matter what is the injection ratio of the adversary, the system will never be stable. Okay. So these are two of our results. This is not an exhaustive list of them, and if you're interested in our results and in the technical details of our work, so please go to our document, our paper, or send us an email to any of the address that is in the contact information. Thank you very much for your attention.